following is an integrative analysis of an inversion structure within the Subandean Ucayali Basin in Peru. We will utilize various techniques along with previous interpretations of seismic data from Wine et al. 1995 to create a forward model in which additional quantitative information can be calculated. Performing a sequential structural restoration to key horizons in the section will allow us to unravel the general structural development in which to use as a framework for subsequent modeling. Restoring first the upper top pozo horizon reveals an earlier stage of contraction prior to the deposition of the upper stratigraphic units. This can be seen by the fold shape of the Juruá Disconformity, as well as the cross-fault thickness change of the Triassic sediments. Furthermore, we can see that the upper units involved in the latest stage of contraction are most likely pregrowth, as they have comparable thicknesses on both the hanging wall and footwall. Continuing the sequence of restoration down section and restoring the Juruá Disconformity reveals the early rift architecture of the structure. Starting with the single segment fault model with Trishear fault propagation enabled for the upper segment of the interpreted fault, we can begin interactively modeling the well-imaged upper fold of pregrowth strata. Adding structural surfaces to the model in their footwall positions, we can specify rough ages for the surfaces, which will be used in order to model erosion associated with the development of the structure. We can then contract the upper surfaces to their hanging wall cutoffs and adjust Trishear parameters for a better model fit. Continuing the fault down section, we adjust the fault geometry to better match the fold shape and regional depths of interpreted horizons. Adding the oldest surface representing the basement depth next will give us an overall structural envelope to work with and a rough outline to constrain the rest of the model. Notice changing the footwall depth of the basement surface affects the upper fold due to the current model using Trishear fault propagation for the entire development of the structure. In this case, we must restrict fault propagation to the contractional stage of deformation, and we can do this by selecting the model surface which represents the onset of fault propagation. Here we will choose the surface representing the latest phase of contraction to initiate Trishear fault propagation folding. The previous basement interpretation requires too much rollover of the footwall, and therefore the footwall correlation can be adjusted to comply with the model which was constructed based on the geometry of the well-imaged upper fold shape. At this stage in the analysis, we can animate the model to see if our structural envelope represents inversion correctly. Adding more surfaces to the model, we adjust the hanging wall and footwall positions to reproduce the fold shape and unconformable geometries observed in the hanging wall. Using this convention, we can continue adding and manipulating structural surfaces to match the seismic data. Here we are attempting to reproduce the hanging wall cutoff and angular unconformity by adjusting the footwall position of a horizon in which the previous interpretation has it removed from the footwall. We can model an eroded footwall surface as represented by the dashed structural surface, and furthermore reconstruct footwall stratigraphy that has been completely removed by reproducing key geometric characteristics of the hanging wall fold shape observed from the seismic data. Animating once more, we can see the development of the entire modeled structure at a rate proportional to the ages specified in the model. Finally, with ages defined in the model, we can produce burial history diagrams calculated from the thicknesses and ages of structural surfaces, which display the complex depositional history of the structure.